We're going to start by being a little bit more specific with our summation notation that we could use to write for an area under a curve. We should be able to look at this and now understand that we can use an integral to represent the infinite sum of very skinny rectangles starting at -2 and going to 2 under the function. And that would represent the area that's shaded. And of course, if you don't want to use f of x, you can use the equation 4 minus x squared, and it's the same thing. When you use 4 minus x squared, you should put parentheses around it, just so that you kind of know that it's the infinite sum of these heights times the consistent width. Now, again, where did the integral come from? It is a replacement notation for this. The limit as n approaches infinity of the sum with values, we denote the values as i's, starting at 1 and going to n, and representing the amount of objects, of my function values, so f at xi's, so the xi's denotes like which height I'm using, times delta x being the width of my objects. And without this limit as n approaches infinity, what we have is a right Riemann sum. If I just hid this part of it, that's a right Riemann sum, which is, an approximate area for a finite n. If we use an infinite n, then it becomes exact area. And what we do is instead of using this, we use the integral. But what is required of you on the AP exam is to be able to write this area using this notation. We need to be a little bit more specific. We can't just say, oh, this area is here. We need to denote which function we're using and from where to where. And how are we going to do that using this notation? Well, we can start by understanding that the function is 4 minus x squared. And I could say, so I'm going to say using f of x is equal to 4 minus x squared. And then from -2 to 2, I could say this is equivalent to the limit as n approaches infinity of the sum I starting from 1 and going to n of 4 minus xi squared times delta x. Okay, and all of a sudden we are using this notation with this function. Okay, we need to be comfortable with that. But what we do not have is the fact that we are going from -2 to 2. We need to be able to incorporate that into this because it is incorporated in here. And you might say, well, it's in the delta x, but right now we just know it as delta x. So, and instead of xi's, we can replace that with something to denote where we are starting with our right Riemann sum. So here's the ticket to go from here to what we want to see as our final answer. We need to recall that delta x is just b minus a over n. And this x sub I is actually our starting point plus whatever value we're using times delta x. It just tells us like how far are we going over to use what height for our right Riemann sum. And if we have a finite, if you start with a and you add say like 8 delta x's, you'd end up at the end of your segment, depending on what delta x is, if you're using 8 as n. Okay, so this is the key, and we will actually use this in here. Now, using A as -2 and B is 2, I can rewrite this as 2 minus -2, or 4 over n, and xi can be written as -2 plus I times that delta x, which we wrote as 4 over n. We can take this information and substitute it here, and we will have the correct summation notation for the area under this function from -2 to 2. Let me show you what it would look like. It would be the limit as n approaches infinity of the sum by starting at 1 going to n of 4 minus -2 plus, I'm going to put the I next to the 4 just for notation's sake, 4i over n squared times 4 over n. And again, it's going to be, and what we should have had up here is parentheses, because we were summing up our right heights and then multiplying that by our consistent width. So I'm going to put parentheses here. This, my friends, is something that you need to be able to produce for an AP exam. It looks far more complicated than it is, so long as you understand. So long as you understand what goes in it, it's not that bad getting here. If you know what delta x is, and actually the new thing is understanding what the x sub I is. Now we have that to make it a right Riemann sum. Okay, so this whole thing is the same as the integral from -2 to 2 of 4 minus x squared dx. You need to be prepared to express area under a curve both ways. Okay, so let's go ahead and practice that once. Writing the area of this shaded region both as a sum using summation notation and using integral notation. Okay. You can see why people started using integral notation pretty quickly instead of the summation notation. Okay, look up and check your answer whenever you're ready. But there's my summation notation, and obviously that is my integral notation. Okay. Questions? It's not too bad, but once we get to the AP test, a lot of people forget the whole delta x, b minus a over n, and xi being a plus I delta x. So it's a problem that a lot of students get wrong. Okay, moving on. We're going to talk about some properties of these integrals, these definite integrals, okay? And we're going to start out just making sure we understand how we read and say this, okay? This is read the integral from a to b of f of x dx. Okay, and we know this is an infinite sum of heights times widths, but it ends up being the exact area between a curve and the x-axis. So the function or the curve and the x-axis might not always be a curve, as we know. Here's a bunch of straight lines. Now, typically, A will be the smaller number compared to B. A, then B. However, that won't always be the case. Sometimes you'll have an integral from B to A, and we'll have B down here and A down there. What's really important is that they are different, and that order matters. An integral from A to B is not going to be the same as an integral from B to A. But we'll see how they're related. A is the start, B is the end. Make sure you understand we are starting at the bottom value, we are finishing up at the top value. So we start at A and we go to B. That's why it's read from A to B. The order matters. Okay? And why does it matter? It's because direction is important on the x-axis. Let's look at just really quickly if we have the function going from left to right above the x-axis. I'm going to the right. We create these really skinny rectangles. The heights are positive. Well, we actually say that the widths are also positive because I'm traveling from A to B. I'm going in the positive x direction. So the integral from A to B is just a bunch of positive heights times positive widths, giving me that positive area. And conversely, if we look underneath the x-axis, it's going to be positive widths but negative heights. I'm going from left to right, so my dx is positive. However, my function values are negative, which is why we say when we're under the x-axis, this area is negative, because I'm negative heights, positive values. Okay? Now, this is the case if we are looking at the curve here to the left and to the left. As long as we're above the x-axis, we are good. It does not matter if we are to the left or the right of the y-axis. This is still the case. Positive above the x-axis, negative below the x-axis. But let's flip-flop them. Question so far. If we're above the x-axis, we're positive. If we're below the x-axis, we are negative. If we flip-flop and we go from right to left, from B to A, what do you think the area is going to be compared to the area from A to B? It will be the opposite. Let's think about that really quickly. If I'm going from B to A, I'm traveling to the left on the x-axis. That is a negative direction on the x-axis. My function values, if we're above the x-axis, are still positive. So I would say the integral from B to A would be positive heights times negative widths, giving me a negative area. Okay? And if we went from B to A below the x-axis, turns out the area would end up being positive. We had negative heights, but we'd be going in the negative direction, so the dx would be negative. So we'd consider this positive. Giving us our first property that if we have the area from A to B, it's going to be equal to the opposite of the area from B to A. Order matters. If I'm going from right to left, it is going to be opposite of the area from left to right. So if I have an integral from 1 to 3 of f of x that I know that's equal to 5, I can easily say that the integral from 3 to 1 of f of x will be negative 5. Okay, that's property number 1. Order matters. Pay attention to order. Next one. What if I go from A to A? So here's A. I'm trying to find the area starting from A and going to A. So from A to B, we know we have some area. If I bring B and I put it right on top of A, so it's A to A, discuss what you think that answer is going to be. Go. All right, Mr. Wong, what do we get?
You said that it would be 0.
Yes, that is correct. There's no area. We start and end at the same place. This is our second property. If I have an integral from 5 to 5 of any function, even if it's curved, well, this is something that you can now answer. It's definitely 0. Okay, the third one. I'm just going to give you the property right now, and then I'll just make sure you understand it. If you have a constant, next to a function, you are allowed to pull the constant out and multiply the constant by the area under the function. Constants may be pulled out. Okay. If I look at this, I can kind of see that. The area from 1 to 3 under f of x is equal to 2. This area here is 2. Well, if I looked at the area from 1 to 3 of 3 times f of x, we would think that the area is 3 times the area that I know. So that'd be 3 times 2, which is 6. I can confirm that this area is 6. So checks out. Constants may be pulled out. You could take this 3 and you just move it out. if it simplifies things. Okay. The next one you guys will be able to figure out yourselves. If I have the area from a to b, so the integral from a to b of f of x dx, and I add the integral from b to c, what do you think that equals? Discuss with your neighbors. Go. What do you think, Swans? Yep. What do you think, Ms. Keithley? Yes, it'll just cover all of the area from A to C. That's easy enough. Another one that you could probably guess, but I'll just tell you. If you have a bunch of functions being added or subtracted, you can actually split them up. It's a very, very important one when we're doing some practice problems we're about to do. If you have a complicated thing, but you know kind of the individual areas, we could split them up and add them separately. Functions being added may be split into multiple integrals. Okay. Bringing us to the next one. If I have a constant, finding the area under the constant from A to B, I gave you an example. The constant is 3 from 1 to 5. Can we come up with some property where we always know what this will be? Okay, discuss that with your neighbor. Go. What do you think, Mr. McCausey? Yes. What specifically is delta x in this case? Yeah. Using the values a and b. Yes, exactly. K, which is the height, times b minus a. It's just a rectangle of area. So we know this area here is 3 times 4, which is 12, right? So I just take the height and multiply it by our, our width, our delta x. Excellent. So again, if I want the integral from 1 to 5 of 3, I know this is just going to be 3 times 4, which is 12. Okay, brings us to the next one, something that a lot of students will trip up on, which I don't want you to trip up on. If I have a constant being added to my function, let's say this area right here is 3. A lot of people say, oh, if I want to find the area from 1 to 3 of f of x plus 3 dx, I'll just take the area from 1 to 3, and then I'll add 3. and they say, okay, this area is 3, add 3, my answer has got to be 6. They just almost look at this and they say, oh, the area under F is 3, add 3, I get 6. Okay? This is wrong. And this is wrong. Why? Because using kind of both properties at the same time, this should be split up to 2 different integrals. And you're not just adding 3. You're adding a rectangle's worth of area, which has a height 3 and a width of 2. We should be adding 6. Okay? To show that, just use the 2 properties that we just talked about. You can split this into f of x plus the integral from a to b of k, and now that'll be the area under f plus k times b minus a. So it's not just plus k. Okay, so actually this will be 3 plus 3 times 2, which is 6, giving me that this area here is 9. Okay, does that make sense? When you shift everything up, you add a rectangle's worth of area. Height 3, width 2 to the already existing area of 3. So don't just add constants to areas.
How would we know the difference between like adding something to a function and having a function that just has a constant in it, like plus 4? Would it tell us like find the integral of f of x plus 4, so then we would know that it's separate from the function itself?
Yes, you will be given something like this.
Mm-hmm.
But what I'm telling you is maybe if you have this, and you know that the integral from 0 to 1 of x squared is a third. So let's just say you were told that. You don't know why that's the case. Then you'd say, oh, it's not 1/3 plus 2. Oh, that stinks. It is 1/3 plus 2 in this case. Let's switch that to this, and this becomes 4/3. No, 8/3. Sorry, you don't know why, but this area from 0 to 2 under x squared is 8/3. If I give you this question here, you would not say it's 8/3 plus 2. You would say, oh, it's going to be 8/3 plus 2 times 2, which is 4. That makes sense? So you can kind of use the information you know, and then just make sure you're not adding 2 to it.
Yeah, but we could have a function in theory that's just x squared plus 2, like as the actual function. Like that's x.
I won't give you that unless I told you what the area under x squared is, because you don't know how to find that yet.
Oh, right, okay.
Okay, because it's a curve. You will know by the end of the last lesson in this unit. Okay, that's it. We're ready to do some examples, some practice. I don't have much time to do it, but we'll have enough time to do enough. What we have is information that will be given to us when we have problems like this. Like this guy and this guy. That's the information. Using those 2 pieces of information, you should be able to answer these 6 questions. Okay, you don't have to write them all down, but I want you to try to work through them to get the answers. So like the first one, the integral from 5 to 0 of f of x dx. Okay, we know that has got to be the opposite of the integral from 0 to 5. So I know this answer has got to be -10. That's easy enough. This one, it's the integral from 7 to 7. Well, starting and ending at the same point, I know this has to be 0. Okay, you guys do the other 4. When we get to this one, this is like the toughest one that we'll see. My advice is to do the problem with the values going from left to right first. Then once you get that answer, then just take the opposite of it, because we notice we're going from 7 to 5, not from 5 to 7. Okay? Let's see what we get. Start checking your answers with a neighbor. Okay, the first 4 should have been fairly straightforward. 25, 13, -9. The last one, what I like to do is start with it as the flip-flop, knowing that my answer is going to be opposite. Okay, so I do have f of x minus 2. Don't change that sign. The integral should be split up to f of x and then to the minus 2. Take the opposite of all of that. So the f of x is 3. And then the minus 2 would be multiplied by 2, would give us -4. So it'd be 3 plus -4, but the opposite of that. We end up with just 1. Okay? Let's do this one. For this one, we'd have to do the first one. To do the second one, I'm giving you 3 pieces of information that are given to you. I get -5 for the first one. Why? I change this by pulling it out, divide both sides by 3. I get that the area from 0 to 5 of f is 2. That means the area from 0 to 5 of f minus g would be 2 minus 7, which is -5. Now the second one asks me for the area from 0 to 3. Well, I have 0 to 5, 0 to 5, and 3 to 5. How am I going to find 0 to 3? Well, it's the whole a to b plus b to c gives you a to c. 0 to 3 plus 3 to 5 will give me 0 to 5. 0 to 5 I found, it was -5. 3 to 5 is 2. That means 0 to 3 has to be -7. Okay, that's the idea for a lot of your homework that is out of the book tonight. I'm going to show a couple more examples for the video. All right, let's finish off with a couple using a graph. First one, let's skip and go straight to the second one. Doesn't matter what the function looks like. This will be 0. I go from 5 to 0 of -3f of x. Well, I like to just immediately say I'm going to go from 0 to 5, and nothing changes. But we make sure that the answer is the opposite. I can take that -3 and pull it out, which means it'd be the opposite of -3, which would make it +3 times my area from 0 to 5. What's my area from 0 to 5? Well, let's see. This is a trapezoid with 2 heights, 1 and 2, so this is 3. This is a rectangle, 4. This is a triangle, area is 1. This area down here is -2, so 3 times the area from 0 to 5. This is 8 times 3, which would be 24. And then 5 to 7 of f of x plus 3 would be the same as the opposite of the area from 5 to 7. Sorry, 7 to 5. And then this would be from 5 to 7. Again, I would split this up so that I have the area from 5 to 7, which is -2, plus the area under a straight line, height 3, width 2, that would be 6. So this would be 4, and then I'd take the opposite of it to give me -4. Okay, so I'd get -4, 0, and 24 for those last 3. That's it. Thank you.